back to my channel. Today we're going to be going through the detailed notes for the carbon cycle and energy security revision unit over here on my channel. It's the EdXL specification, but I am sure this will be helpful for all of the specs. I have done 9 of these so far up on my channel. I will dot them throughout the video. I'll link one up whichever side it is, I still don't know 2 years later, but I will link one of them and then they all kind of link to each other. But I have 2 left. I have this one and then I have the diverse places one to do, so I will hopefully get them up for you within the next couple of weeks. But yeah, there's one more after this one. But today we are going through the carbon cycle and energy security unit. So grab yourself a notebook, grab your revision notes, or grab a snack and just sit and listen to me talk at you for a little bit. I hope it's helpful. Please do leave any comments or questions that you have about this unit, or any exam questions that you're doing on this unit, and hopefully I can put a video together, put them all together and share it with you. So I hope this has been useful. For a bit of context of why I'm doing this, I wanted this during my A-levels. No one was doing this online. I'd seen it for biology and other subjects, but when I was doing my A-levels 3-4 years ago now, wow, yeah, no one was doing it, so I thought I'd do it myself. Once I graduated uni, I did a degree in geography and education studies, with the hopes of becoming a teacher. I'm not doing that at the moment, but hopefully next year. So yeah, that's where we're at. That's why I'm doing this. I hope it is helpful, but without further ado, let's get straight on into this video. The geological carbon cycle. The natural carbon cycle is the movement and storage of carbon between land, ocean and the atmosphere. There are 3 forms of carbon in the carbon cycle. Firstly, inorganic. This is found in rocks and bicarbonate as carbonates. There's organic carbon, which is found in plant material and living organisms, and then gaseous carbon, found as CO2 and CH4, methane, in the atmosphere. There is generally a balance between production and absorption, or sources and sinks, of carbon in the natural carbon cycle. Sometimes, however, it does take a long time for equilibrium to be reached, such as after a volcanic eruption. Stores are terrestrial, oceanic or atmospheric. Fluxes refer to the movement or transfer of carbon between the stores. The stores of the carbon cycle. A carbon sink is any store which takes in more carbon than it emits. So an intact rainforest is an example. A carbon source is a store that emits more carbon than it stores. So a damaged tropical rainforest is an example of that. Carbon is present in stores of the atmosphere as CO2 or methane, the hydrosphere as dissolved CO2, the lithosphere as carbonates in limestone, in fossil fuels like coal, gas and oil, and the biosphere in living and dead organisms. Carbon sequestration is the transfer of carbon from the atmosphere to other stores that can be both natural and artificial. For example, a plant sequesters carbon when it photosynthesizes and stores carbon in its mass. The main carbon stores in order of magnitude. Firstly, marine sediments and sedimentary rocks in the lithosphere, long term. This is easily the biggest carbon store. 66,000 to 100,000 million billion metric tons of carbon. The rock cycle and continental drift recycle rock over time. This may take thousands, if not millions, of years. The oceans. These are in the hydrosphere and this is a dynamic store. This is the second biggest store and contains a tiny fraction of the carbon of the largest store. 38,000 billion metric tons of carbon. The carbon is constantly being utilised by marine organisms, lost as an output to the lithosphere, or gained as an input from rivers and erosion. Fossil fuel deposits. The lithosphere, and these are long-term but currently dynamic. Fossil fuel deposits are used to be rarely changing over short periods of time, but humans have developed technology to exploit them rapidly. Though 4,000 billion tonnes of metric carbon remain in fossil fuels. Soil organic matter. This is found in the lithosphere and it's a mid-term store. The soil can also store carbon for over 100 years, but deforestation, agriculture and land use change are affecting this store. 1,500 billion metric tons of carbon are stored here. And the atmosphere, this is a dynamic store. Human activity has caused CO2 levels in the atmosphere to increase by around 40% since the Industrial Revolution, causing unprecedented change to the global climate. This store holds 750 billion metric tons of carbon. And terrestrial plants in the biosphere, mid-term but very dynamic. These are vulnerable to climate change and deforestation, as well as a result of carbon storage in forests declining annually in some areas of the world. 560 billion metric tons of carbon are stored in these stores. The lithosphere is the main store of carbon, with global stores unevenly distributed. For example, the oceans are larger in the southern hemisphere, and the storage in the biosphere mostly occurs on land. Terrestrial plant storage is focused in the tropics and in the northern hemisphere. Fluxes of carbon cycle. The transfers in the carbon cycle act to drive and cause change in the carbon cycle over time. They all have impacts of varying magnitude over different lengths of time. Biological and chemical processes determine how much carbon is stored and released. The role of living organisms is also very important in maintaining the system and helping it run efficiently. Photosynthesis. Living organisms convert carbon dioxide from the atmosphere and the water from soil into oxygen and glucose using light energy. By removing CO2 from the atmosphere, plants are sequestering carbon and reducing the potential impacts of climate change. The process of photosynthesis occurs when chlorophyll in the leaves of the plant react with CO2 to create carbohydrate glucose. Photosynthesis helps to maintain the balance between oxygen and CO2 in the atmosphere. Respiration. Respiration occurs when plants and animals convert oxygen and glucose into energy, which then produces the waste products of water and CO2. It's therefore chemically the opposite of photosynthesis. I keep getting tripped up on that. During the day, plants photosynthesize, absorbing significantly more CO2 than they emit from respiration. During the night, they do not photosynthesize, but they do respire, releasing more CO2 than they absorb. Overall though, plants do absorb more CO2 than they emit, so they are a net carbon dioxide absorber from the atmosphere and net oxygen producers to the atmosphere. Combustion. When fossil fuels and organic matter such as trees are burnt, they emit CO2 into the atmosphere that was previously locked inside of them. This may occur when fossil fuels are burnt to produce energy or if wildfires occur. Decomposition. When living organisms die, they are broken down by decomposers, such as bacteria, which respire, returning CO2 into the atmosphere. Some organic matter is also returned to the soil, where it is being stored, adding to carbon matter of the soil. Diffusion. The oceans can absorb CO2 from the atmosphere, which has increased ocean acidity by 30% since pre-industrial levels. The ocean is the biggest carbon store, but with carbon levels increasing seawater becomes more acidic and is harming aquatic life by coral bleaching. Many of the world's coral reefs are now under threat. Sedimentation. This can happen on land or in the sea. For example, when a shelled marine organism dies, their shell fragments fall to the ocean floor and become compacted over time to form limestone. Organic matter from vegetation and decaying marine organisms is compacted over time, whether on land or in the sea, to form fossil fuel deposits. Weathering and erosion. Inorganic carbon is released slowly through weathering. Rocks eroded on land or broken down by carbonation weathering. Carbonation weathering occurs when CO2 in the air mixes with rainwater to create carbonic acid, which aids erosion of rocks such as limestone. The carbon is moved through the water cycle and enters the oceans. Marine organisms use the carbon in the water to build their shells. Increasing carbon dioxide levels in the atmosphere may increase weathering and erosion as a result, potentially affecting other parts of the carbon cycle. Metamorphosis. Extreme heat and pressure forms metamorphic rock, during which some carbon is released and some becomes trapped. Volcanic outgassing. There are pockets of CO2 found in the Earth's crust. During a volcanic eruption, or from a fissure in the Earth's crust, this CO2 can be released. Variation in carbon fluxes. The quickest cycle is completed in seconds, as plant absorbs carbon for photosynthesis, and then they release carbon when they respire. This cycle can slow down when levels of light or CO2 drop. Dead organic matter in soil may hold carbon for hundreds of years. Some organic materials may become buried so deeply that they don't decay, or are buried in conditions that are unfavourable to decayers, potential low-lying gas or too much water. This material will become sedimentary rocks or hydrocarbons by geological processes. Complete carbon processes. Oceans are the largest carbon stores. They are 50 times larger than the atmosphere, with 93% of CO2 stored in oceanic algae, plants and coral. Lots of processes occur simultaneously within the ocean to store these large amounts of CO2. This transfer of CO2 into the ocean is called ocean sequestration. Small changes in oceanic carbon levels have significant global impacts. The CO2 gas exchange between the atmosphere and the ocean operate on different timescales. It's important to note that the ocean has different layers. The majority of the processes which take the CO2 out of the atmosphere and occur in the top ocean, out of the atmosphere and into the top of the ocean occur in the top surface layer, which makes up only a small proportion of the water in the world's oceans. The carbon-rich water layer, surface layer, is then transferred down to the lower layers of the ocean and transported around the world due to thermohaline circulation. This is the circulation which allows such large amounts of carbon to be stored in the sea. The biological carbon pump. Phytoplankton are microscopic organisms that, like plants, photosynthesize. They take in carbon and turn it into organic matter. As they are the base of the marine food web, half of the planet's biomass consists of phytoplankton, despite their microscopic size. When they get eaten, carbon is passed through the food chain. Remember that CO2 is also released back into the water as these organisms respire. Some organisms, like plankton, sequester CO2, turning the carbon into their hard outer shells and inner skeletons. When these organisms die, some of their shells dissolve into the ocean water, meaning that the carbon becomes part of the ocean deep sea currents. Any dead organism which sinks to the seafloor become buried and compressed, eventually forming limestone sediments through sedimentation. Over a long time period, these can turn into fossil fuels. At the same time, some CO2 from the atmosphere will be naturally dissolving into the water. This process occurs on the surface of the ocean, where CO2 reacts with water to form carbonic acid. As the concentrations of CO2 in the atmosphere increase, oceans absorb more CO2, causing them to be more acidic. This acidification of the oceans could have long-lasting effects. This movement of CO2 isn't one way. Some will go from the water back into the atmosphere. The physical pump. There will come a point where the surface layer of the ocean will become so saturated with carbon that this process will slow down or stop occurring. However, oceanic circulation provides a constant source of new water on the surface, while transferring surface water into the deep ocean. It's this process which enables the ocean to store so much carbon. Water is not stored evenly within the Carbon is not stored evenly within the water. The colder the water, the more CO2 is absorbed, so the concentration of CO2 in the ocean is different around the world. CO2 concentration is 10% higher in the deep ocean compared to the surface of the ocean. Polar regions hold more carbon than the tropical regions. Warm tropical water releases CO2 into the atmosphere, but cold, high-latitude oceans absorb CO2 from the atmosphere. Thermohaline circulation. Thermohaline circulation is an ocean current that produces both vertical and horizontal circulation of warm and cold water around the Earth's oceans. In addition to this, the atmospheric circulation creates large currents in the oceans, which transfers water from the warmer regions to the colder polar regions. The rate of circulation is slow. It takes around 1,000 years for any cubic metre of water to travel around the entire system. Warm surface waters are depleted of CO2 and nutrients, and therefore the foundation of the planet's food chain depends on cold and nutrient-rich water, which supports algae to grow. Water in the North Atlantic is cold and very saline, which means it's denser and heavier, causing it to sink. When the cold water sinks, warm water is drawn up to the ocean surface. Eventually, cold water is drawn from the bottom of the ocean and then warmed up. The process in more detail. The main current begins in the polar oceans, where the water is very cold. Surrounding seawater sinks due to higher density. The current is recharged as it passes the Antarctica by extra cold, salty, dense water. Division of the main current as it passes the Antarctica by extra cold, salty. Division of the main current northward to the Indian Ocean and southern to the West Pacific. The two branches warm and rise as they travel northwards, then loop back southward and westward. The now warmed surface water continues circulating around the globe. On their eventual return to the North Atlantic, they cool and the cycle begins again. The rate of absorption of CO2 into the oceans depends on ocean temperatures. The colder the water, the more CO2 that is absorbed. Therefore, as ocean temperatures increase, the oceans will absorb less CO2, possibly even emitting some of its stored carbon dioxide. This will accelerate climate change and leading to further ocean warming, a positive feedback mechanism. The role of the oceans in regulating climate and greenhouse gas emissions is essential to the Earth. Terrestrial sequestration. Primary producers sequester carbon. Primary producers, plants, sequester carbon through the process of photosynthesis. All living things either release or intake carbon. Primary producers take carbon from the atmosphere to photosynthesize and release carbon when they respire. Vegetation growth depends on water, nutrients and sunlight. When consumers eat plants, carbon from the plants is converted into fats and proteins. Microorganisms feed on material waste from plants and animals. Animal and plant remains are easier to decompose compared to wood. Decomposition is faster in tropical climates with high rainfall, temperatures and oxygen levels. 95% of trees' biomass consists of CO2, which is sequestered and converted to cellulose. The amount of carbon stored in trees depends on the balance of respiration and photosynthesis. Carbon fluxes due to terrestrial organisms vary. They vary diurnally. During the day, fluxes are positive from the atmosphere to the ecosystem, whereas in the night, fluxes are negative from the atmosphere to the ecosystem. They also vary seasonally. In the northern hemisphere during winter, plants die and decay, leading to high atmospheric CO2 concentrations. But during spring, when plants begin to grow, CO2 levels in the atmosphere begin to drop. Different amounts of carbon are stored worldwide, and one of the stores that is actually changing is trees. I'll show you this picture. This map shows how forests are declining in the tropical areas in the southern hemisphere and growing in the northern hemisphere. This is supported by data which shows that tropical areas such as Brazil and Indonesia have seen a decrease in carbon stocks of around 5 gigatons of carbon in the last 25 years. But Russia, the USA and China have seen increases of 0.3, 2.9 and 2.3 gigatons respectively. Detailed information on tropical forests and climate change shows that non-tropical forests have seen an increase in carbon sequestration in recent years, especially in Europe and Eastern Asia, due to conversion of agricultural land and plantations to new forests. Forests in industrial areas are expected to increase by 2050, but in the global south, forested areas will decrease. Rates of forest loss have also decreased, from 9.5 million hectares in the year 1990 to 5.5 million in the years between 2010 and 2015. The eight countries with the largest forested areas are Russia, Brazil, China, Canada, the USA, the Democratic Republic of Congo, Australia and Indonesia. Brazil has the most stored carbon on land and the most extensive deforested area. China has the largest amount of afforested area. Net primary productivity refers to the amount of carbon absorbed by forests. For tropical forests, it is positive all year round, but deciduous forests have a negative NPP in winter, but across the whole year the NPP is positive. Soil capacity to store carbon. Soils store between 20 and 30% of the world's carbon. The amount of CO2 sequestered or emitted depends on local conditions. In arid or semi-arid soils are the most important stores. Any loss by a plant to the ground means that some carbon will transfer to the soil. Soil microbes break down plants and release carbon to the atmosphere. After organisms die, thousands of compounds in soil are decomposed. The most long-term process in the formation of humus is the formation of humus. It has a dark, rich colour and 60% of it contains carbon. Factors affecting soil capacity to store organic carbon include the climate, which affects the rate of plant growth and microbial activity, and decomposition occurs at a fast rate in places with higher temperatures and rainfall. Soil type. Clay-rich soils contain more carbon than sandy soils, and the use of soils. Land use, cultivation and disturbance can affect how much carbon can be held. If plant residue is added to the soil at a faster rate than soil organisms can convert it to CO2. Carbon will eventually be removed from the atmosphere and sequestered into the soil. The natural greenhouse effect. The Earth has a temperature control system which relies on the greenhouse gases in the atmosphere. The Earth's climate is driven by incoming short-wave solar radiation. Around 31% is reflected by the clouds and gases into the atmosphere. The remaining 69% is absorbed by the Earth's surfaces and oceans. 69% of surface absorption is re-radiated to space as long-wave radiation. A large proportion of long-wave radiation is radiated back to the Earth by the clouds and greenhouse gases. Constant levels of CO2 help to maintain a stable average temperatures worldwide. Before the Industrial Revolution, the natural greenhouse effect was constant. The slow carbon cycle, volcanism, sedimentation have been fairly constant over the last few centuries. Natural exchanges between the slow and fast sections of the carbon cycle were relatively small, and there were small variations in atmospheric CO2 until the late 19th century. Anthropogenic interference. A balanced carbon cycle is very important in maintaining other global systems. The enhanced greenhouse effect. Since the 1750s, when industrialisation began in the UK, global concentrations of greenhouse gases like CO2 and CH4 have increased by more than 25%. Since the 1980s, 75% of carbon emissions have come from burning fossil fuels. Human activities have led to more carbon being released into the atmosphere and less being absorbed. Land use change accounts for a tenth of carbon released annually and impacts on short-term stores in the carbon cycle, such as the soil and the atmosphere. For example, farming practices in the Amazon. Around 70% of deforestation is for cattle ranching. Cattle produce a significant amount of methane, further contributing to global warming. Scientists are considering whether feeding cows different food would help to reduce their methane emissions. Fertilisers are also a significant source of greenhouse gases, as well as rice paddy fields, from which methane emissions have increased as a result of increased productivity due to higher CO2 levels. More suitable grains and seeds like quinoa are being considered as substitutes, which require less water to grow. Deforestation. In total, deforestation accounts for about 20% of all greenhouse emissions. The main impact is when the carbon cycle is interrupted and the land is used for other purposes, which then reduces carbon sequestration and land becomes a carbon source rather than a carbon sink. Urbanisation. This is the process of replacing countryside with buildings and other similar infrastructure. It affects the local and global carbon stores by replacing vegetation and covering soils. Urban areas occupy 2% of the world's landmass, but these areas account for 97% of all human-caused global CO2 emissions. Cement is an important building material, but releases carbon dioxide during production, contributing to 7% of global carbon dioxide emissions each year. So sustainable options for recycling concrete are being developed. Combustion of fossil fuels. This results in CO2, sulphur and particulates being released into the atmosphere. If combustion occurs in a hot engine, NO2 will also be released, also a greenhouse gas, as nitrogen from the air fuses with oxygen. The amount of carbon is measured in gigatons or petagrams. It is estimated that burning fossil fuels has added more than 180 gigatons to the carbon of the atmosphere. Increasing levels of greenhouse gases can affect the planet's climate, which can have implications for the water cycle, biomes and wildlife living on Earth. Implications of the enhanced greenhouse effect. Temperature. The amount of solar energy reaching the Earth varies depending on location and is the main factor in determining climate temperatures. Solar intensity is more intense at the equator and reduces as you travel towards the poles. The albedo effect will also determine the temperature of a location. Snow reflects solar radiation, whereas dark forests absorb the most solar radiation. Climate. Rising CO2 levels in the atmosphere are believed to be the main contributor to an increase in global temperatures across the globe. However, increases may vary. In Europe, average temperatures are expected to increase more than the global average. The largest increases are expected in Eastern and Northern Europe during winter and Southern Europe during summer. Annual precipitation is expected to increase in Northern Europe, but decrease in Southern Europe. Extreme weather events are likely to increase both in frequency and intensity. Precipitation. Solar radiation is most intense at the equator, so convectional rainfall is common and rainfall is generally very high. Where convectional rainfall is most likely to occur can be understood using the ITCZ model. Rainfall occurs at subtropical highs, mid-latitudes and the poles. When air submerges and cools, water vapour condenses to form clouds and precipitation. Where air rises, the air heats up and moisture will evaporate. This can create dry weather conditions. Ecosystems. Ecosystems help to regulate the carbon and hydrological cycles. Global warming could impact the functioning of ecosystems. The two biomes most at risk are the Arctic and coral ecosystems. Species with low population numbers are already at high risk. There is already evidence showing that there will be change in species, population size, timing of reproduction and migration. Marine organisms are also at risk. They are threatened with low oxygen levels and high rates of acidification. The impact on coastal ecosystems and low-lying areas of sea levels rising could continue. The Arctic region is warming twice as fast as the global average. Melting permafrost releases methane and carbon dioxide, which increases concentration of greenhouse gases into the atmosphere. This could lead to further global warming and even more melting of snow and ice, establishing a positive feedback loop. The Arctic tundra ecosystem has significantly changed. Rapid warming has contributed to extensive melting of snow and ice during the summer months. Shrubs and trees which previously couldn't live in the Arctic have begun to grow. In Alaska, the red fox has now spread northwards and competes with the Arctic fox for food and territory. Not all scientists agree that permafrost melting will release CO2 and CH4. Some studies show that when permafrost melts, the carbon may remain in the soil and warmer temperatures lead to more decomposition, which uses CO2. The hydrological cycle. There is an increased an increased rate of evaporation could lead to more moisture being held in the atmosphere rather than in the ocean. There is an increase in surface permafrost temperatures, less sea ice and glacier storage, change in capacity of terrestrial ecosystems, and there's a change in river discharge, and an increased risk of flooding in winter and droughts in the summer. Energy security. Maximum energy security refers to uninterrupted availability of energy resources at an affordable price. Long-term energy security mainly deals with timely investments to need to supply energy in sources that will match economic development and environmental needs. Short-term energy security focuses on the availability of energy system to react promptly to sudden changes in the balance between energy and demand and energy and supply. There are several key points worth remembering about energy security. It's generally evaluated at a national level. Countries are either energy secure or insecure. There are 4 aspects of supply: availability, accessibility, affordability, and reliability. It requires an accurate prediction of future energy, and those countries that are most energy secure are those who can meet their energy demand using supply from within their boundaries. A good quality energy supply is consistent and secure and can be relied upon year-round. There is unlikely to be any geopolitical problems, and there is little risk from changing climatic conditions or natural hazards. A good quality energy supply involves different sources, which contribute to the energy mix. Energy security is important for functioning of the country, and particularly its economy, including the operation of most modes of transport, lights in towns and cities, heating homes, domestic appliances, and it's necessary for most forms of manufacturing. Measuring energy usage. Energy consumption is usually measured per capita per person on the following measures: equivalent kilograms of oil per year, gigajoules per year or exajoules, or megawatts per hour, or megawatts per year. There we go. Megawatt hours per year, that's what I'm trying to say. Energy insecurity is an alternative measure of how efficiently a country is using its energy, in costs of energy used per unit of GDP. A high energy intensity indicates a high price or cost of converting energy into a GDP. It's generally recognised that energy intensity decreases with development. Energy is used more efficiently, and so the cost per unit of GDP reduces. The energy mix. The energy mix refers to a range and proportion of energy produced by methods of production. These can include non-renewable fossil fuels like oil, gas and coal, recyclable fuels like nuclear energy and general waste, and renewable energy like wind, solar and geothermal. The global energy mix is dominated by fossil fuels. Primary energy sources produce energy using a raw material, whereas secondary sources are modified primary sources, which are easier to use, e.g. petrol into coal and electricity. Primary energy sources. Coal accounts for 27% of global energy production. Usage is decreasing as China shifts its energy mix away from coal and less polluting energy sources are used. Most production occurs in China, ahead of the USA and India. Petroleum, oil, accounts for 32% of global energy production. Usage is still increasing as global energy demand increases. The most usage is in the USA, China and India, with greater production in the USA, Saudi Arabia and Russia. Natural gas. With only 50% of carbon emissions of coal and accounts for 22% of global energy production, which is increasing year on year. The highest production is in the USA, Russia and Iran, and the greatest consumption is in the USA, Russia and China. Uranium has a very low carbon footprint that accounts for 4% of global energy production, with the most production in Kazakhstan and greatest amount of nuclear fission energy produced in the USA. Production is likely to increase in the future. Biomass. This may also be secondary. In many low-income countries, biomass is burned to produce energy. Burning organic matter such as wood is very inefficient. However, biomass produces a large proportion of energy in LICs, though it makes up a low proportion of worldwide energy consumption. In higher income countries, biomass is being used more efficiently to produce energy, such as biodiesel. There is an overall decrease in use on a global scale. Hydroelectric power. Water drives turbines to produce electricity and is very efficient. Hydropower has been used for many years as a renewable source of energy, but only accounts for a very small percentage of global energy production. This is expected to increase globally, but would decrease in some HICs. Solar. Solar energy usage is increasing rapidly year on year as the technology for solar power becomes cheaper. China has the largest installed capacity, though production is much lower due to climatic conditions. Growth in LICs as technology becomes cheaper. Wind. Other than hydropower and biomass, this produces the most energy of renewable sources, with greatest production and capacity in China. Technology is also spreading to LIC countries and offshore is increasing too. Wave. Very low generation, though technology is developing and a similar trend may be seen of that of solar and wind when the technology becomes cheaper. Tidal. So expensive that there is only a handful of installed tidal power systems on a global scale. The Swansea Bay scheme was abandoned due to the potential cost that it would induce. One successful project may lead to a multiplier effect. Geothermal energy. This is very efficient and reliable and operates on an all year round day and night basis. Popular in countries with a volcanic setting and is likely to increase as technology spreads to LICs. It does not currently contribute a large amount to the global energy mix though. Global consumption varies, but it is generally higher in Northern Hemisphere countries which are more developed. Global energy demands and trends by type of energy production are shown in these pictures, and you can explore it more using the links down below. Energy players. There are key players who have important roles in securing energy pathways and controlling prices. They explore, exploit and develop energy resources. They own supply lines and invest in the distribution and processing of raw materials, and they respond to market condition to increase the profits. Most energy players are TNCs, although there are some exceptions, such as Russia's state-run Gazprom. Some names of key energy players include Saudi, Amacron? I don't know how to pronounce it. Russian Gazprom, BP in the UK, Shell, UK and Netherlands, ExxonMobil, which is in the US, Petrobras in Brazil, Gazprom in Russia, and PetroChina in China. TNCs are the most prominent energy players for a variety of reasons. Some TNCs have more economic value than a small country, enabling the company to take action and invest large-scale projects that a country cannot afford. TNCs can bypass political tensions and access sources otherwise restricted by other countries. In certain parts of the world, an MEDC trying to help exploit an energy source in an LEDC could be seen as a threat to the LEDC. TNCs may be inclined to invest in local infrastructure, logistics and development of workers' villages. This benefits all. The TNCs benefit from faster transport links and a happier workforce, while the government receives free investment. Of course, TNCs aren't always beneficial. TNCs may encourage environmental degradation, exploiting workers, and unsustainable transportation. OPEC. OPEC is an IGO with member communities which exploit oil and petroleum. OPEC producers control 81% of the world's discovered oil reserves. Their mission is to unify the petroleum policies of its members to ensure the stabilisation of oil markets. They also want to create an efficient and regular supply of oil to its consumers, a steady income for producers, and a fair return for those investing in the industry. In the past, OPEC set quotas depending on the condition of the world economy. Supplies were boosted when demands rose, while supplies were cut when demand fell. Between 2012 and 2016, oil output was kept high to compete against the USA, which produced vast amounts of oil due to fracking. The flooding market caused a collapse in global oil prices. OPEC had been accused of holding back production in order to increase prices and in turn increase profits for oil exporting nations. This can be detrimental to developing countries who need vast, cheap amounts of oil to continue economic development and manufacturing. National governments. Governments try to secure supply secure energy supplies for their country, and they also regulate the role of private companies. EU governments are trying to reduce CO2 emissions and reduce dependency on fossil fuels. Consumers. Consumers create demand, with purchasing choice usually based on price. As a country becomes richer and more educated, the population can change their shopping habits to reflect their needs, locally sourced, environmentally friendly, reliable energy supply during winter and extreme weather. For example, lots of energy companies have now set tariffs on imported or non-renewable sources to reduce energy insecurities or carbon offset their energy. Here, money raised on non-renewable energy can fund environmental work such as afforestation, research into carbon capture and storage. If consumers change their spending habits and only use these tariffs, then companies will be encouraged to move towards more green energy. Consumers can have an impact on TNCs. The effect of human geography on energy supply. Most countries are interdependent for energy sources. They import energy from other countries. This has geopolitical implications and requires the cooperation from other countries. At any stage of the energy supply chain may be used by countries as a political tool to cause or resolve tension between countries. Different countries have varying national interests. TNCs may help if there are good links with countries, who can then compensate for a building through a pipeline through their landscape. Alternatively, TNCs may be forced by powerful governments to spend additional money on protecting a landscape, even if that would make no economic sense to the TNC. However, it would provide a natural gas pipeline and improve political relationships. Energy supply can be a very confusing process, influenced by physical and human geography, TNCs, geopolitics, community groups and activists. You'll need a case study that concerns energy supply and these factors. Problems with achieving energy security. Fossil fuel supply. There is a mismatch between the supply and demand for fossil fuels. This is largely due to inequality of wealth and development, natural resource supplies and industrialisation. Consumption of coal is declining worldwide, more than other fossil fuels. Over half of the world's oil comes from APEC and North American nations. However, since Europe has the largest demand for oil but produces very little oil, it must be transported and traded. This may cause further insecurity and tensions. Energy pathways. There are many ways of transporting energy between countries. Here are some pathways and their weaknesses. Pipelines are efficient in carrying billions of meters cubed of oil across the world and many countries. Many of these pathways depend on international agreements, so influence global politics. Around half of the world's oil is transported using an oil tanker through choke points, a key point in the logistics of energy, which can be easily disrupted. If choke points become blocked or threatened, then oil prices can rise very quickly and political tensions escalate. In this map, Ukraine is considered a choke point in the EU's supply of oil. Most pipelines from Russia run through Ukraine, and with increasing uncertainty in Ukraine and relations in Russia, the EU supply could become increasingly insecure, which is why we have seen increasing oil prices and gas prices and electricity prices since the Ukraine war broke out this time last year. Political conflict. Conflicts and political altercations can severely limit energy security. For example, military conflict can destroy infrastructure, which will restrict the flow of energy from source to use. Disagreements between nations will also limit energy security. This is the case for Russia, who have several political sanctions against them. As Russia is a major supplier to Europe, this has caused some shortage in electricity. Alternative energy sources. Within the last decade, new and unconventional energy sources have become more realistic. Some alternative sources aim to increase supply of fossil fuels, keeping energy prices low and improving energy security. However, some new alternative sources aim to reduce CO2 and greenhouse gas emissions while still meeting demand. Unconventional fossil fuels. Shale gas, which is extracted using fracking, has received major environmental opposition. However, it provides 25% of the US's energy needs in 2015. Fracking is a relatively new process of extracting shale gas. Water, chemicals and sand are pumped into the ground to break up the shale. access the hydrocarbons and force them to the surface. Horizontal drilling helps to remove gas reserves. There are benefits and costs of fracking. The advantages: it's less polluting than coal and oil, requires a large amount of water, can provide boosts to the economy, and in the UK, the Royal Academy of Engineers believe we can make fracking safe. But the disadvantages: wastewater needs treating due to the chemical contents. It may pollute the groundwater aquifers. In the USA, water has become flammable due to pollution by fracking. Earthquakes of low magnitude may occur. Though they are not usually strong enough to pose a risk to humans, they may damage fracking infrastructure, causing further leakages. And the IPCC suggests it would be irresponsible to use shale gas. Deepwater oil. As oil supplies decrease, energy companies have begun extracting oil from deeper depths. Deepwater oil faces larger risks during extraction, similar to normal oil production, oil spills during transportation. The advantages: many engines and appliances are designed to operate in oil, and therefore to continue to extract oil would avoid large changes to many important engines, such as vehicles, planes, etc. Tar sands. The extraction of petroleum from sands involves high energies and boiling water, which can leave ponds of concentrated chemicals. Tar sands have large environmental costs, but can be lucrative in profit and employment opportunities. They create economic growth and large influx of jobs for rural regions, and is a fast-growing industry, producing the high-value bitumen for international exportation. And the disadvantages: the volume of extracting bitumen is water and energy intensive, producing a large volume of waste. The liquid waste is left in tailing ponds, so water can be recycled after it separates from the clay and salts. However, tailing ponds may also contain sulfate, chloride and ammonia, which may infiltrate into groundwater stores and other water sources. Open mining involves removing the top layer of vegetation and soil to access the bitumen sands, destroying habitats. Alternatives to fossil fuels. As reserves of oil and gas begin to diminish, new reserves and technologies are being developed to support further resource exploitation. Currently, new reserves are being discovered at a lower rate, rather than immediately exploited. Environmental groups suggest that fossil fuel exploration should stop immediately and renewable energy used instead. In countries like Bahrain, which is 75% reliant on oil for their GDP, this is not an economically viable or sustainable solution. Renewable energy. Renewable energy is likely to be an important component of future energy mix, as it has a low carbon footprint. The technology is always improving and becoming more efficient. Each renewable resource has advantages and disadvantages, though as time progresses the disadvantages should decrease as the technologies are improved. All have the disadvantage of being visually unappealing and causing minor disturbances to the local environment. Examples of new development in renewable technologies to research are solar, concentrated solar power, solar-powered roads, solar roof tiles, wind power, so vortex blades, larger blades and offshore, wave power, eco-wave power and Pelamis wave power, tidal power, so the Swansea Bay, but this was abandoned, tidal stream, major tidal stream project, and then geothermal, Forge and the enhanced geothermal system. However, not all countries have renewable energy sources due to their physical geography, such as lack of wind, sun, rivers, etc. Many people claim that renewable energy can completely replace non-renewables, but this is unlikely, because not all renewable sources provide the same amount of energy. You need more wind turbines than hydroelectric dams. Oil prices in 2015 dropped significantly as renewables are generally more expensive. They became less attractive. Some forms of renewable energy have negative impacts, such as HEP could lead to large swathes of land being flooded. Nuclear power. Nuclear power is considered to be a recyclable energy, since uranium is needed to produce large amounts of energy through fission. Despite being the most realistic option for replacing fossil fuels, there are some risks to nuclear energy. Nuclear disasters like Chernobyl and Fukushima, mainly due to mismanagement, could happen again. the risk that nuclear power stations may be infiltrated during conflicts by terrorists. Radioactive waste has to be disposed of safely, often through vitrification in underground caverns. And the technology involved is only accessible for developed countries. Operational costs are quite low, but construction and decommissioning costs are extremely high. Energy security may be compromised if countries own and fund these nuclear plants in other countries. Biofuels. Biofuels, in theory, are a good alternative to fossil fuels. The process of burning biofuels is carbon neutral. CO2 taken in by plant during photosynthesis will then be released during combustion. However, across the globe, forests have been cleared to plant oil palms in Malaysia, oilseed rape in the EU, and maize in the USA to manufacture biofuels. There are many environmental implications with deforestation for biofuels. Loss of biodiversity and habitats, reduced vegetation to intake CO2. In addition, clearing land to grow biofuels creates food insecurity. Many Swiss, Swedish and American companies have bought land in order to grow biofuel crops, but this has infiltrated land prices. A shortage of food in 2001 in Mexico led to the tortilla riots. Corn was bought by TNCs to produce biofuel for cars, which increased the price of corn, making it unaffordable for Mexican families to buy food to eat. Reducing carbon emissions. There are several strategies to try and take some CO2 out of the atmosphere or reduce emissions. However, these tend to be expensive and must be carried out on a national scale to take effect. Carbon capture and storage is a technological strategy used to capture CO2 emissions from coal-fired power stations. The gas collected from the power plant is compressed and stored into underground aquifers or disused mines. CCS could help to reduce carbon emissions by 19%, but due to their cost, only one scheme exists currently. Hydrogen fuel cells provide an alternative to the use of oil. Hydrogen is the most abundant element in the atmosphere, and it usually combines with other elements such as carbon. Therefore, hydrogen needs to be separated and stored before use. Fuel cells convert chemical energy found in hydrogen into electricity, and this produces pure water as a byproduct. These fuel cells are much more efficient than petrol engines in vehicles. Across the globe, there are contrasting threats and demand to the land, water supply and carbon fluxes. Deforestation. Forests cover about 30% of the Earth's land area. Forests intercept rainfall and increase groundwater storage. A loss of even a small number of trees can disrupt weather patterns and could lead to more intense flooding and droughts. More than half of forested land is cleared due to increased demand for commodity production, soy, palm oil, beef and paper production. Land is also being built to convert dams and reservoirs. Therefore, land clearing may increase as energy demands increase and water supplies decrease. By 2015, 30% of all global forests have been cleared. Annually, around 13 million hectares are lost every minute. The impacts on the water cycle. There's less interception, so more surface runoff and a shorter lag time. A shorter lag time will increase flooding risk, more soil erosion as there's no tree roots to bind soil together, eroded material in rivers and less evaporation from vegetation. The impacts on the carbon cycle. There is a reduction in carbon stored in the biosphere, reduction absorbed by photosynthesis, and more carbon released from combustion. Regional trends. 90% of forests in the UK and USA were lost through deforestation in the 19th century. Boreal forests have been threatened in Russia and Canada for oil and tar sand production. In Africa and South America, most forests have been halved in area since the 1960s. In Indonesia, large amounts of forests have been cut down or burnt to make way for palm oil plantations, which demand is increasing significantly. Implications for human well-being. Over 1.6 billion of people depend on forests, and more than 90% of these people are amongst the poorest in society. Between 2000 and 2010, deforestation affected 13 million hectares of forest every year. Many people joined pressure groups like Greenpeace and the WWF to oppose forest loss. Greenpeace found that TNCs don't do enough to prevent deforestation, forest fires and human rights abuses. Grassland conversion. There are two main types of grasslands. Temperate grasslands, which have no trees, and tropical grasslands or savannas, which have trees but infertile soil. Their role. They trap moisture and floodwater, absorb toxins from the soil, provide cover for dry soils, provide habitats for wildlife, act as a carbon sink. The impacts on the carbon cycle. Converting grasslands into agricultural farms will release CO2 into the atmosphere initially. There is a net increase in CO2 emissions as biofuel drop and need fertilisers, and cultivated soil is more susceptible to erosion. Ocean health. Oceans absorb around 30% of the atmosphere's CO2. Since 1800, around 50% of all emissions came from the combustion of fossil fuels. As CO2 in the ocean increases, the pH of the ocean decreases, increasing acidity. Overfishing is also creating an imbalance in ocean health, threatening ocean security in the future. Fishing supports 500 million people, of which 90% live in LICs. Fish is a cultural choice for many wealthy MEDCs, where it is necessary for people in LEDCs. Millions of small-scale fishing families depend on seafood for their income as well as for their food. In addition to fishing, many countries rely on the marine life to attract tourism. Therefore, overfishing and ocean acidification can have direct consequences for a country's economy and employment. Impacts for wildlife. As oceans become more acidic, corals cannot absorb alkaline in order to maintain their skeletons, and in turn reefs begin to dissolve. Algae provide food to corals through photosynthesis. If the water becomes warm, though, the algae leaving the coral to turn white, known as coral bleaching. Coral reefs shelter 25% of marine species, protect shorelines, support fishing industries, and provide an income through tourism. Climate change. Increasing the world's climate emissions are enhancing the greenhouse effect significantly, and this is affecting the world's climate. There are more frequent and more intense storms and hurricanes, there are rising sea levels, therefore more coastal erosion and some land loss, known as isostatic sea rise, and there are more frequent floods, droughts and heat waves. Changes in ocean currents and atmospheric circulation could have an impact on patterns of precipitation, evapotranspiration and temperature. Scientists have used climate model simulations to investigate shifts in climatic zones. They believe that for the increase of 2 degrees, 5% of the Earth's land area shift to a different climatic zone. In 2015, there were some unusual weather patterns. There were droughts in parts of Africa, Pakistan and India, flooding in the USA and Europe, and warmer temperatures in Russia and Siberia. Greenhouse gases are likely to increase in the future as more countries industrialise and develop. Greenhouse gases remain in the atmosphere for a long time, and so even if the global emissions were reduced, surface air temperatures would still continue to rise. It's very difficult to predict future emissions, and so scientists use various scenarios to project greenhouse gas concentrations. There are several uncertainties in estimating future climate change, but they have identified several tipping points and feedback mechanisms that scientists believe would accelerate climate change. Uncertainty over climate change. Oceans and forests are climate stores. Oceans take a very long time to respond to changes in greenhouse gas concentrations. Weather will have a direct influence over vegetation productivity and the rate of chemical reactions. As how climates will change is unknown. Future vegetation changes is also unknown. Alternatively, human factors will create the most uncertainty predictions. Economic growth, which increases CO2 emissions. Population change, as increasing affluence in emerging economies mean there will be an additional 1 billion consumers, which could lead to more emissions and more energy consumption. And then technology and globalisation leads to more travelling and transportation of goods, which produces more emissions. Feedback mechanisms. Negative feedback dampens the original process of feedback loops, whilst positive feedback loops amplify the original process. Both of these accelerate climate change. Peat is the accumulation of partly decayed vegetation, which stores large amounts of carbon. Warming causes peat to dry out and the rate of decomposition increases. An increase of 4 degrees causes a 40% loss of soil organic carbon from shallow peat and 86% from deep peat. Peatlands emit carbon in the form of methane, which increases greenhouse gases and accelerates enhanced greenhouse effects. Permafrost. When permafrost melts, trapped carbon is released into the atmosphere as CO2, and methane, which increases greenhouse gas emissions into the atmosphere. This leads to higher temperatures and further melting of ice. Tipping points. A climate tipping point is a critical threshold. When this threshold is reached, small changes in the global system can transform a stable system irreversibly. Forest dieback. Rainfall in the Amazon is largely recycled. If there is a drought in the rainforest, trees may die. A tipping point could be reached when moisture can no longer be recycled due to too many trees taking moisture, which leads to more trees dying. In the boreal forest ecosystem, hot and dry summers lead to water stress, which can result in a loss of trees. A tipping point could be reached when they no longer absorb CO2 and in turn increase the concentration of greenhouse gases in the atmosphere, leading to further dry summers. Thermohaline circulation. Cold water in the North Atlantic forms part of the thermohaline circulation. To keep the warm water from heading towards the tropics towards Britain, heavy water must sink from the north. The melting of the northern ice sheets releases large amounts of fresh water into the ocean, which is less dense and of low salinity. This will disrupt circulation of the water, affecting the temperature of the ocean reaching the ocean, and in turn the weather of the UK. It's believed that some scientists that the thermohaline circulation is slowing down. If it stops, the world will go into another ice age. And that is the end of this very long video. I hope you are still here. I hope you have found it useful. As I say, leave any exam questions down below and I will upload one of these videos going through kind of how I'd answer it, a bit of the structure. We'll look at the mark scheme and go from there. So I hope this has been useful. Please do subscribe down below if you're still here. I upload these sporadically and I upload more geography videos throughout the rest of the weeks. But yeah, I hope you found this useful. Thank you for watching and I'll see you soon.